Tonight I want to take you somewhere extraordinary, somewhere that exists between the realm of the possible and the impossible, where light itself, that most fundamental force of nature that has travelled freely through the universe for billions of years, was brought to a complete standstill. Not slowed down, not dimmed, but actually stopped, frozen in place like a photograph of motion itself. For 60 seconds, in a laboratory that might as well have been a cathedral to human curiosity, scientists achieved what should have been impossible. They caught light and held it still, suspending it in a crystalline cage of atoms cooled to temperatures that barely exist in nature. I wonder where you are right now as you listen to these words. Perhaps you're nestled in bed, the day's concerns slowly dissolving into the quiet of evening. Maybe you're in Tokyo, where the city lights still flicker against the night, or in London, where the rain taps gently against windows, or somewhere in the countryside where stars peek through gaps in clouds. Whatever time zone cradles you, whatever corner of this spinning planet you call home, you found your way here to explore one of the most remarkable achievements in modern physics. And if these journeys into the cosmic mysteries help you drift into peaceful sleep, while feeding your curiosity about the universe, perhaps you'd like to follow along for more of these nocturnal explorations. Consider subscribing if you'd like to join me regularly as we unravel the universe's secrets together, one quiet wonder at a time. It's a question that might sound strange at first, something you could easily dismiss as science fiction or impossibility. How can anyone stop light when its very nature is to move at the ultimate speed limit of the universe? But the more we look at it, the more quietly intriguing it becomes. What if stopping light wasn't just a laboratory trick, but a gentle doorway into understanding how reality itself can be bent, shaped, and transformed when we learn to speak the universe's most fundamental language? You see, light has been our companion since the beginning of everything. From the first photons that escaped the cosmic soup of the early universe to the gentle rays that warm your face on a spring morning, light has always been in motion, always travelling, always carrying information across the vast emptiness of space. Every star you've ever seen, every colour that has ever caught your eye, every sunset that has ever taken your breath away, all of it has been light in perpetual motion, racing at 300,000 kilometers per second, a speed so fundamental to the fabric of reality that Einstein built his greatest theories around its constancy. And yet, in a small laboratory at Harvard University, a team of physicists led by Lena Howe achieved what generations of scientists would have deemed impossible. They didn't just slow light down, though that alone would have been remarkable. They brought it to a complete stop, holding it suspended in a cloud of sodium atoms cooled to temperatures just billionths of a degree above absolute zero. For 60 seconds, an eternity in the quantum world, light that had been racing through space became perfectly still, its information preserved, its properties intact, waiting patiently to be released back into motion. The story of how they accomplished this feat takes us deep into the strange realm of quantum mechanics, where the rules we know from everyday experience gently dissolve into something far more fluid and mysterious. It begins with understanding that light, despite our everyday experience of it, isn't quite what it seems. We think of light as brightness, as illumination, as the thing that reveals the world to us. But light is both simpler and more complex than our intuition suggests. It's electromagnetic radiation, waves of electric and magnetic fields oscillating through space. But it's also composed of particles called photons, packets of pure energy that somehow manage to be both wave and particle simultaneously. This dual nature of light has puzzled physicists for centuries. How can something be both a wave spreading out through space and a particle located at a specific point? The answer lies not in choosing one description over the other, but in accepting that light, like so much in the quantum world, exists in a state of gentle ambiguity until we observe it and force it to reveal one aspect or another of its nature. This strange duality would prove crucial to understanding how scientists could eventually grab hold of light itself. The journey towards stopping light began not with an intention to freeze photons in place, but with a desire to understand how light interacts with matter at the most fundamental level. Scientists knew that when light passes through any material, glass, water, even air, it slows down slightly. This slowing isn't because the photons themselves are moving more slowly. Individual photons always travel at the speed of light. Instead, What happens is that photons are absorbed by atoms, held for an infinitesimally brief moment, then re-emitted in the same direction. This constant absorption and re-emission creates the illusion of slower light, much like how a person walking through a crowd appears to move more slowly even though their individual steps maintain the same pace. But in most materials, this slowing is modest. Light travelling through glass moves at about 2/3 its vacuum speed. Through water, it's about 3/4. Even in the densest, naturally occurring materials, light still races along at speeds that dwarf anything in our everyday experience. To truly slow light down, to bring it to speeds we could actually observe, and eventually to a complete stop, scientists would need to create conditions that don't exist naturally anywhere in the known universe. The key insight came from understanding that atoms themselves could be manipulated, their properties tuned like instruments in an orchestra, to interact with light in precisely controlled ways. At normal temperatures, atoms are in constant motion, vibrating and colliding with each other in a chaotic dance that makes precise control impossible. But as you cool atoms down, their motion slows. Cool them enough, down to temperatures approaching absolute zero, the theoretical point where all atomic motion ceases, and something remarkable happens. The atoms begin to behave not as individual particles, but as a collective entity, a state of matter known as a Bose-Einstein condensate. This state of matter, predicted by Einstein and Satyendranath Bose in the 1920s, but not created in a laboratory until 1995, represents one of the most exotic conditions we can create. In a Bose-Einstein condensate, atoms lose their individual identities and merge into a single quantum entity, like drops of water combining into a perfectly still pool. The atoms move in perfect synchronization, creating a material with properties that seem to belong more to the realm of magic than physics. It was in this ethereal state of matter that Lena Howe and her team first achieved the impossible. In 1999, they had already stunned the physics world by slowing light down to just 17 meters per second, about the speed of a car in a residential neighborhood. They achieved this by shooting a pulse of light into a cloud of sodium atoms cooled to within billionths of a degree of absolute zero and held in place by magnetic fields. The cloud, no bigger than a cigar, had been carefully prepared using a technique called electromagnetically induced transparency. This technique is worth dwelling on for a moment, as it reveals the beautiful choreography involved in manipulating light. Normally, sodium atoms would absorb light at certain frequencies, making the cloud opaque. But by shining a carefully tuned control laser into the cloud, Howe's team could create a kind of quantum interference that made the atoms transparent to a specific frequency of light, while still allowing them to interact with it. It's like creating a material that light can pass through, but that still grabs onto the light as it passes, slowing its journey without stopping it entirely. The control laser essentially creates a narrow pathway through the forest of atoms, a channel where light can propagate but only by constantly interacting with the surrounding atoms. These interactions slow the light dramatically, but in 1999, the light still moved forward, still maintained its essential nature as something in motion. The breakthrough of completely stopping light would require an even more delicate manipulation of these quantum systems. By 2001, Howe's team had refined their technique to achieve what had once been thought impossible. They discovered that by carefully adjusting their control laser, gradually reducing its intensity while a light pulse was inside the atomic cloud, they could transfer all the information carried by the light pulse into the atoms themselves. The light didn't just slow down, it ceased to exist as light altogether. Its information, its quantum state, its properties, everything that made it a particular pulse of light, was written into the collective quantum state of the atoms. For 60 seconds, what had been a racing pulse of light became a stationary pattern encoded in the delicate quantum arrangement of sodium atoms. The atoms held the light's information like a photograph holds an image, preserving every detail in their collective quantum state. Then, by turning the control laser back on, they could release this stored information, converting it back into light that continued on its way, as if nothing had happened, carrying the same information it had held before its minute-long pause. Think about what this means for a moment. Information that normally travels at the ultimate speed limit of the universe was brought to a complete standstill, held in quantum suspension, then released to continue its journey. It would be like catching a whisper in a jar, holding it there perfectly preserved, then opening the jar later to let the whisper continue to its intended listener, unchanged by its captivity. This achievement opened up possibilities that stretch far beyond the laboratory. The ability to stop and store light could revolutionize how we process and transmit information. Current fiber optic communications rely on converting optical signals to electronic ones whenever the information needs to be processed or stored, then converting back to light for transmission. Each conversion introduces delays and potential errors. But if we could stop and store light directly, we could create purely optical computers and communication systems, processing information at the speed of light without the bottleneck of electronic conversion. The implications extend into the realm of quantum computing, where the fragile quantum states that carry information are notoriously difficult to preserve. Stopped light could serve as a kind of quantum memory, holding quantum information in a stable state until it's needed. This could be crucial for building quantum networks where quantum information needs to be transmitted over long distances, stored at relay points along the way without losing its delicate quantum properties. But perhaps the most profound implications are not technological, but philosophical. The fact that we can stop light forces us to reconsider what we mean by fundamental constants and unchangeable laws of nature. The speed of light in vacuum remains constant and unsurpassable, but we've learned that light's journey through the universe is far more negotiable than we once believed. We've discovered that with the right conditions, the right understanding, and the right tools, we can convince light to pause its eternal journey, to rest for a moment in our carefully prepared quantum trap. This achievement also highlights the strange relationship between light and matter at the quantum level. When light is stopped in a Bose-Einstein condensate, where exactly does it go? It doesn't accumulate somewhere like water behind a dam. Instead, it transforms, becoming a pattern in the quantum state of atoms, existing in a form that isn't quite light and isn't quite matter, but something in between, something that reveals the fluid boundary between energy and matter, between motion and stillness, between the possible and the actual. The stopped light experiments have continued to evolve since those first breakthroughs. Scientists have learned to stop light in different materials, at slightly higher temperatures, for longer periods. They've developed techniques to stop light in one location and retrieve it from another, effectively teleporting the information carried by the light pulse. They've even learned to slow and stop light in materials that could potentially be integrated into practical devices, moving these phenomena out of the exotic conditions of near absolute zero temperatures and into conditions that might one day be achievable in everyday technology. Each advancement reveals new facets of light's nature and our ability to control it. We're learning that light, which has always been our window into the universe, our fastest messenger, our most reliable constant, is also surprisingly malleable when we understand the quantum rules that govern its behavior. The universe, it seems, has left room for negotiation even with its most fundamental phenomena. Consider for a moment the photons streaming from your screen or lamp right now, racing toward your eyes at the universal speed limit, carrying the information that creates the image you see. These photons, descendants of the same physical laws that govern starlight and cosmic radiation, could theoretically be stopped, held in quantum suspension, their journey interrupted by the same techniques that Howe's team pioneered. The light by which you read these words contains within it the potential for stillness, for pause, for a moment of quantum rest before continuing its appointed rounds. This duality, light as both unstoppable force and something that can be tamed, reflects a deeper truth about the universe. What seems absolute from one perspective reveals flexibility from another. What appears to be a fundamental limitation might simply be an invitation to deeper understanding. The universe operates not by rigid laws carved in stone, but by elegant principles that reveal new possibilities as our understanding deepens. The atomic clouds that can stop light are teaching us about more than just the nature of light itself. They're showing us how quantum mechanics operates at a scale we can observe and manipulate, bridging the gap between the microscopic quantum world and our macroscopic experience. When a pulse of light is stopped in a cloud of atoms, we're witnessing quantum mechanics writ large, seeing effects that normally hide in the realm of individual particles played out in systems we can observe and measure. The preparation required to stop light is itself a testament to human ingenuity and patience. Creating a Bose-Einstein condensate requires cooling atoms to temperatures that barely exist in nature, colder than the space between stars, colder than the cosmic microwave background that pervades the universe. Scientists achieved these temperatures through a combination of laser cooling and evaporative cooling, techniques that took decades to develop and refine. Laser cooling might seem paradoxical. How can light, which we normally associate with heat and energy, cool something down? The answer lies in the momentum carried by photons. When atoms moving toward a laser absorb photons, they slow down, like balls thrown upward against gravity. By surrounding atoms with carefully tuned lasers from all directions, scientists can gradually rob them of their kinetic energy, cooling them to temperatures just millionths of a degree above absolute zero. But even this isn't cold enough to create the conditions needed to stop light. The final cooling requires evaporative cooling, the same principle that cools your skin when water evaporates from it. By allowing the most energetic atoms to escape from the trap, scientists can cool the remaining atoms even further, reaching the billionths of a degree above absolute zero needed to form a Bose-Einstein condensate. In this ultra-cold environment, the sodium atoms behave in ways that would seem impossible at normal temperatures. They overlap with each other, their quantum wave functions merging into a single entity. Individual atoms lose their identity, becoming part of a collective quantum state that responds to light in precisely controlled ways. It's in this delicate, ephemeral state that light can be convinced to stop its eternal journey. The control laser that creates the transparency window in the atomic cloud operates on principles of quantum interference. By carefully tuning its frequency and intensity, scientists create a situation where the probability amplitudes for light absorption cancel out, creating a narrow pathway through which light can pass. But this pathway isn't just empty space. It's a carefully structured quantum environment where light moves by constantly interacting with the atoms around it, like a person moving through a crowd by gently touching each person they pass. When the control laser is gradually turned off while light is inside the cloud, something remarkable happens. The light doesn't just disappear or get absorbed in the usual sense. Instead, its quantum state is mapped onto the collective state of the atoms. The atoms remember everything about the light, its phase, its amplitude, its quantum correlations. They hold this information in their collective quantum dance, preserving it perfectly until the control laser is turned back on and the light is regenerated. This storage and retrieval of light represents a new kind of memory, fundamentally different from how we normally store information. In conventional computer memory, information is stored as patterns of electrical charge or magnetic orientation. But in stopped light, information is stored in the quantum state itself, in the delicate correlations between atoms that can preserve not just classical information, but quantum information, with all its strange properties of superposition and entanglement. The potential applications of stopped light extend far beyond communication and computing. Scientists envision using stopped light to create new kinds of sensors, able to detect incredibly faint signals by accumulating them over time. They imagine quantum networks where information can be transmitted with absolute security, protected by the laws of quantum mechanics from any eavesdropping. They see possibilities for studying fundamental physics, using stopped light to probe the nature of time, causality, and the relationship between light and matter. But perhaps even more important than these practical applications is what stopped light teaches us about the nature of physical laws. We tend to think of the laws of physics as constraints, as limitations on what is possible. The speed of light seems like an ultimate boundary, an impassable wall built into the fabric of space-time. But the stopped light experiments show us that physical laws are more subtle than simple prohibitions. They're more like the rules of a complex game, full of unexpected strategies and surprising possibilities for those who understand them deeply enough. The fact that we can stop light without violating any fundamental laws of physics reveals the richness hidden within those laws. Einstein's relativity isn't overturned by stopped light. The speed of light in vacuum remains constant and unsurpassable. Instead, we've discovered that the interaction between light and matter contains possibilities that Einstein himself might not have imagined, even as his theories predicted them. This is how science progresses, not by overthrowing everything that came before, but by finding new depth in established principles. The equations of quantum mechanics, written down nearly a century ago, contained within them the possibility of stopped light. But it took decades of theoretical and experimental work to reveal this hidden potential. Who knows what other surprises lurk in the equations we already know, waiting for the right insight, the right experiment to bring them to light. The 60 seconds during which light was first stopped might seem brief, barely enough time to boil water for tea. But in the context of light's usual behavior, it's an eternity. Light that would normally travel far enough to circle the Earth 4.5 times instead remained perfectly still, suspended in a cloud of atoms smaller than your thumb. It's a pause in what has been an uninterrupted journey since the birth of the universe, a moment of stillness in billions of years of motion. During those 60 seconds, the information carried by the light pulse existed in a kind of limbo, neither moving nor lost, suspended between existence as light and existence as matter. The atoms holding this information were like a quantum photograph, capturing not just an image, but the entire quantum state of the light, ready to release it unchanged when called upon. It's a demonstration of the profound unity between light and matter, energy and mass, that underlies the apparent diversity of the physical world. The temperature required to stop light, those billionths of a degree above absolute zero, represents one of the quietest, stillest states we can create in the universe. At these temperatures, the random thermal motion that characterizes normal matter almost completely ceases. Atoms move so slowly that their quantum nature becomes dominant, their wave-like properties spreading out until individual atoms blur into collective quantum entities. It's in this profound quiet, this near-perfect stillness, that light itself can be persuaded to rest. The contrast is striking. Light, the fastest thing in the universe, stopped only in conditions of ultimate slowness and cold. It's as if the universe requires us to create perfect stillness before it will allow its most restless phenomenon to pause. The laboratory becomes a kind of meditation chamber for photons, a place where the eternal motion of light can briefly cease, where the cosmic messenger can rest before continuing its journey. The technical challenges involved in stopping light pushed experimental physics to its limits. The magnetic fields needed to trap and hold the atoms must be precisely controlled, varying by less than 1 part in a million across the cloud. The lasers must be tuned to exact frequencies, stable to better than 1 part in a billion. The vacuum chamber must be emptier than interstellar space, with fewer stray atoms than exist in the void between stars. Every aspect of the experiment requires a level of control and precision that would have been unimaginable just a generation ago. Yet despite these extreme requirements, the basic principle behind stopped light is surprisingly elegant. It's about creating the right conditions for light and matter to exchange roles temporarily, for photons to hand over their identity to atoms and then reclaim it later. It's a kind of quantum hospitality, where atoms provide temporary lodging for traveling photons, preserving their quantum state perfectly during their stay. The success of these experiments has inspired scientists to push even further. They've learned to stop light carrying complex information, not just simple pulses but structured beams carrying images or data. They've stopped light in different kinds of atoms, in solid materials as well as gases, expanding the range of conditions under which this quantum magic can occur. Each new achievement adds another verse to our growing understanding of light's malleable nature. Some scientists are exploring whether stopped light could be used to create a kind of optical transistor, a device that could switch light with light, enabling all optical computing. Others are investigating whether stopped light could help in the detection of gravitational waves or dark matter, using the exquisite sensitivity of quantum systems to detect the faintest whispers from the cosmos. Still others see stopped light as a tool for testing fundamental physics, probing questions about the nature of time, causality, and information. The philosophical implications continue to ripple outward from that first moment when light stood still. If light can be stopped, what else that we consider fundamental might be more flexible than we imagine? If information can be transferred from light to matter and back again without loss, what does this say about the nature of information itself? Is information more fundamental than either light or matter, a deeper layer of reality that can manifest as either energy or mass? These questions take us to the edge of what physics can currently answer, into realms where experiment and theory are still catching up with imagination. But this is where the most exciting science happens, at the boundary between the known and unknown, where careful experiments can reveal surprises that no one anticipated. The atoms that stop light are ordinary sodium atoms, the same element that makes streetlights glow orange and combines with chlorine to make table salt. There's nothing exotic about sodium itself. It's one of the most common elements on Earth. But when cooled to near absolute zero and controlled with quantum precision, these ordinary atoms become capable of extraordinary feats. It's a reminder that the building blocks of the everyday world contain within them the potential for the miraculous, if only we know how to unlock it. The lasers used in these experiments are descendants of technology that was once purely theoretical, deemed impossible by some of Einstein's contemporaries. The laser itself, light amplification by stimulated emission of radiation, relies on quantum mechanics to create coherent light. Light where all the photons march in perfect step. Now we use these quantum devices to control other quantum phenomena, building layer upon layer of quantum technology, each generation enabling possibilities that the previous generation couldn't imagine. When light is stopped, time itself seems to pause for the information it carries. From the perspective of the light pulse, if it could have a perspective, the 60 seconds of stillness don't exist. Time passes only for the rest of the universe while the light's information waits in quantum suspension, preserved perfectly in the atomic memory. When the light resumes its journey, it continues as if no time had passed, carrying its information forward without any awareness of the pause. This temporal discontinuity raises profound questions about the nature of time and information. If information can be removed from the flow of time, held in stasis, then returned to the temporal stream, what does this say about time itself? Is time fundamental, or is it emergent from something deeper? These questions take us into the heart of modern physics, where quantum mechanics and relativity meet and sometimes clash, revealing gaps in our understanding that future generations will need to bridge. The stopped light experiments also demonstrate the power of human curiosity and ingenuity. No practical need drove the first attempts to stop light. No urgent problem demanded this solution. Instead, scientists pursued it because they wondered if it was possible, because the equation suggested it might be, because the challenge itself was irresistible. The practical applications came later, emerging from the pure research like flowers from seeds, planted without knowing what might grow. This is how fundamental science often works, not by solving predetermined problems, but by exploring what's possible, pushing at the boundaries of knowledge to see what lies beyond. The ability to stop light emerged from decades of research into laser cooling, Bose-Einstein condensates, and quantum optics, fields that developed independently before converging to make this achievement possible. No one could have planned this convergence. It emerged naturally from the collective curiosity of thousands of scientists following their questions wherever they led. The cloud of atoms that stops light exists for only minutes at a time, before warming up and returning to normal behavior. The Bose-Einstein condensate is an ephemeral state, requiring constant maintenance and precise control to sustain. Like a soap bubble that exists only as long as conditions are perfect, the quantum state that can stop light is delicate and temporary. Yet in those brief minutes, we glimpse possibilities that might one day become as routine as the transistors in our computers or the lasers in our fiber optic cables. Future historians of science might mark the moment when light was first stopped as a turning point, the beginning of an era when humans learned to control light, not just in its generation and detection, but in its very propagation. Just as the mastery of electrons gave us the electronic age, and the mastery of information gave us the digital age, the mastery of light itself might usher in a photonic age, where information travels and is processed entirely in the optical domain, never needing to slow down to electronic speeds. But even if these practical dreams never fully materialize, the achievement of stopped light has already given us something invaluable, a deeper understanding of the quantum world and our place within it. We've learned that the universe is more flexible than we imagined, that what seems impossible might simply be very difficult, that the laws of physics contain surprises that await discovery by those bold enough to look for them. The laboratory where light was first stopped has become a kind of shrine to human achievement, a place where one of nature's most fundamental phenomena was convinced to behave in an entirely new way. But similar experiments are now conducted in laboratories around the world, each one pushing the boundaries a little further, exploring new materials, new techniques, new possibilities. What was once unique has become reproducible. What was once miraculous has become, if not routine, at least achievable by those with the right equipment and expertise. This democratization of the miraculous is part of science's gift to humanity. What one group discovers becomes available to all, building a collective understanding that transcends individual achievement. The techniques for stopping light are published in scientific journals, discussed at conferences, taught to graduate students who will carry the knowledge forward and perhaps discover something even more remarkable. As you lie there in the darkness, perhaps feeling the weight of sleep beginning to settle over you, consider that the darkness itself is simply the absence of those photons that could, under the right conditions, be stopped in their tracks. The starlight that has travelled for millions of years to reach Earth could, in principle, be paused in its final moments, held in quantum suspension just before completing its cosmic journey. The sunrise that will wake you tomorrow could be delayed, its light caught and held in a trap of ultra-cold atoms, though only for moments before the universe insists on resuming its normal operations. But what is normal, really, in a universe where light can be stopped? Our intuitions about what is natural and what is possible are shaped by the narrow range of conditions we experience in everyday life. We live in a warm world where atoms jostle and collide chaotically, where quantum effects are averaged out into classical behavior. But the universe contains extremes we rarely see: the cold between stars, the pressure inside neutron stars, the quantum realm where particles exist in multiple states simultaneously. Stopped light shows us that these extremes aren't just curiosities but gateways to new phenomena, new possibilities. By creating conditions that don't exist naturally on Earth, we've discovered capabilities that were always latent in the laws of physics, waiting to be revealed. It makes you wonder what other surprises await us as we learn to create even more extreme conditions, to push even further into the realm of the possible. The quantum mechanics that allows light to be stopped is the same quantum mechanics that governs the atoms in your body, the chemical reactions in your cells, the neural processes in your brain. We are quantum beings living in a quantum universe, even if the effects are usually too subtle for us to notice. But occasionally, in experiments like stopped light, the quantum world reveals itself dramatically, showing us the strange and beautiful reality that underlies our everyday experience. The atoms that can stop light are engaging in a kind of quantum dance, choreographed by the laws of physics and directed by human ingenuity. Each atom responds not just to its immediate neighbours, but to the collective state of the entire cloud, moving in harmony like musicians in an orchestra playing a piece of cosmic music. The light pulse enters this dance and becomes part of it, its energy and information absorbed into the collective movement, preserved in the quantum choreography until it's time to resume its journey. This dance between light and matter has been going on since the universe began, but only recently have we learned to observe and control it. Every time light is absorbed by an atom and re-emitted, a brief version of this dance occurs, but in the stopped light experiments, we've slowed the dance down, extended it, made it visible and controllable. We've turned a fleeting quantum moment into a minute long pause, stretching time in the quantum realm to match our macroscopic perception. The control we've achieved over light represents a new chapter in humanity's relationship with the universe. For most of history, we were passive observers of light, dependent on the sun and stars for illumination, unable to do more than block or reflect the light that came to us. The discovery of fire gave us some control over light generation, and the invention of the electric light extended that control. But stopping light represents something qualitatively different, not just generating or blocking light, but controlling its fundamental behavior, negotiating with the laws of physics themselves. This negotiation requires speaking the universe's language, mathematics and quantum mechanics. The equations that describe how light can be stopped are written in the abstract symbols of quantum field theory, describing probability amplitudes and coherent states, Rabi frequencies and dark state polaritons. But beneath the mathematical formalism lies a simple truth. We've learned to ask the universe to do something new, and by asking in the right way with the right preparation, the universe has agreed. The agreement is temporary and conditional. Light can be stopped only under precise circumstances, only for limited times, only in small quantities. The universe hasn't abandoned its fundamental rules, but has shown us flexibility within those rules that we hadn't imagined. It's like discovering that a strict teacher has a sense of humour, that the rigid laws we thought governed everything have room for negotiation if you know how to ask. As the experiments with stopped light continue and expand, we're learning more about this negotiation. We're finding new materials that can slow and stop light, new ways to encode information in stopped light, new applications for this controlled pause in light's eternal journey. Each discovery adds another tool to our quantum toolkit, another way to interact with the universe at its most fundamental level. The implications extend beyond physics into philosophy and even spirituality. If light, that most ethereal and untouchable of phenomena, can be stopped and held, what does this say about the nature of reality? Are there other aspects of the universe that seem immutable, but might yield to the right approach? The success of stopped light experiments suggests that the universe is more malleable than we thought, more open to human influence at the quantum level. Yet this influence remains humble. We can stop light only by creating conditions of extreme cold and precise control, by working with the laws of physics rather than against them. We're not breaking the rules, but finding freedom within them, discovering that the cosmic constitution has amendments we hadn't read, clauses that allow for behaviors we hadn't imagined. The 60 seconds of stopped light represent a kind of meditation on the nature of time and motion. In our everyday experience, time flows continuously, carrying everything forward in an unstoppable stream. But at the quantum level, time becomes more negotiable. Information can be removed from the temporal flow, held in quantum suspension, then reinserted without loss or degradation. It's a glimpse of a reality where time isn't the tyrant it seems, but another dimension that can, under special circumstances, be navigated in unexpected ways. This temporal flexibility might be crucial for future technologies. Quantum computers, which promise to solve certain problems exponentially faster than classical computers, rely on maintaining delicate quantum states for as long as possible. Stopped light could provide a way to preserve these states, creating quantum memory that could store quantum information without the decoherence that normally destroys it. It's like finding a way to stop not just light, but time itself for quantum information, preserving it in perfect fidelity until it's needed. The journey from the first observation that light slows down in materials to the achievement of completely stopped light took centuries of scientific progress. Each generation built on the discoveries of the previous one, adding new understanding, new techniques, new possibilities. The scientists who first noticed that light bends when entering water couldn't have imagined that their intellectual descendants would one day stop light entirely. But their observations laid the groundwork, started the chain of discovery that led, eventually, to that remarkable moment when light stood still. This chain of discovery continues. Today's stopped light experiments will inspire tomorrow's breakthroughs, discoveries we can't yet imagine. Perhaps scientists will learn to stop light at room temperature, making the phenomenon practical for everyday technology. Perhaps they'll discover ways to stop light for hours or days instead of seconds. Perhaps they'll find that stopped light can be used to probe the deepest mysteries of the universe, from the nature of dark matter to the quantum structure of space-time itself. But even without these future breakthroughs, the simple fact that we've stopped light has already changed our understanding of what's possible. We've proven that the universe's most fundamental messenger can be persuaded to pause, that the cosmic speed limit applies to propagation but not to storage, that information can exist in a timeless quantum state, waiting patiently to resume its journey through space and time. As you drift closer to sleep, your thoughts perhaps becoming as slow and quiet as those ultra-cold atoms, consider that you are surrounded by light that could, in principle, be stopped. The gentle glow of streetlights filtering through your window, the faint luminescence of LED indicators, even the thermal radiation invisibly emanating from every object around you. All of it represents photons in motion that science has learned to pause. You live in a universe where such miracles are possible, where human curiosity and ingenuity have unlocked secrets that nature held for billions of years. The atoms that stopped light for those first 60 seconds have long since warmed up and dispersed, returning to their normal existence as ordinary sodium atoms. But the knowledge gained from that experiment continues to propagate, spreading through the scientific community and beyond, inspiring new experiments, new theories, new dreams of what might be possible. The light may have been stopped, but the enlightenment it brought continues to spread at the speed of thought, the speed of inspiration, the speed of human discovery. In the quantum realm where light was stopped, the normal rules of our macroscopic world don't fully apply. Particles can be in multiple places at once, information can exist without a physical carrier, and time itself becomes negotiable. It's a realm that seems like it should be fantasy, but is instead the foundation of reality, the quantum substrate from which our classical world emerges. Stopped light gives us a window into this realm, a glimpse of the strange and beautiful reality that underlies everything we see and touch and know. The precision required to stop light pushes our technology to its absolute limits. The lasers must be stable to frequencies measured in billionths of a wavelength. The magnetic fields must be controlled to strengths measured in billionths of Earth's magnetic field. The temperature must be maintained within billionths of a degree. It's a symphony of precision, where every instrument must be perfectly tuned, every note precisely timed, or the delicate quantum state collapses and the light escapes its trap. Yet despite these extreme requirements, the phenomenon itself is robust. Once the conditions are right, light stops reliably, predictably, following the equations of quantum mechanics with perfect fidelity. It's a reminder that even the most exotic quantum phenomena are governed by laws, by patterns we can understand and predict. The universe may be strange, but it's not arbitrary. It follows rules, even if those rules allow for behaviors that seem impossible from our everyday perspective. The transformation of light into atomic excitation and back into light is a kind of alchemy, transmuting energy from one form to another without loss. But unlike the ancient alchemists who sought to turn lead into gold, modern scientists have achieved something far more valuable: the ability to transform information from one physical carrier to another while preserving its quantum properties. It's not material wealth they've created, but something far more precious in our information age: perfect quantum memory. This quantum memory could be the key to technologies we can barely imagine. Quantum networks that allow perfectly secure communication across any distance. Quantum sensors that can detect the faintest signals from the edge of the universe. Quantum computers that can simulate complex systems from drug interactions to climate patterns with perfect accuracy. All of these possibilities rest on our ability to store and manipulate quantum information, an ability demonstrated dramatically when light was stopped for those 60 seconds. The cloud of atoms that stops light exists in a state of matter that the universe rarely creates naturally. Bose-Einstein condensates might exist in the cold depths of space, in the shadows of molecular clouds where starlight never penetrates, but even there, the conditions are rarely perfect enough. By creating these condensates in the laboratory, we've brought into existence something that the universe itself rarely manages, a state of matter so exotic that it took billions of years of cosmic evolution to produce beings capable of creating it artificially. This is perhaps humanity's greatest achievement, not just understanding the universe but improving upon it, creating conditions and phenomena that nature, left to its own devices, rarely or never produces. We've become co-creators with the cosmos, partners in exploring what's possible within the laws of physics. Stopped light is just one example of this partnership, this collaboration between human imagination and natural law. The implications ripple outward into every area of science and technology. If we can stop light, what else can we control at the quantum level? Can we stop other particles, other forms of energy? Can we create other exotic states of matter with properties we haven't yet imagined? Each success opens new questions, new possibilities, new frontiers to explore. But perhaps the most profound implication is philosophical. Stopped light proves that our intuitions about the universe, formed by evolution in a narrow range of conditions on one small planet, are incomplete. Reality is far stranger, far more flexible, far more wonderful than our everyday experience suggests. We live in a universe where the impossible becomes possible with the right knowledge, where the eternal can be made temporary, where the fastest can be stopped. As sleep approaches, as your own thoughts slow down like light entering that cloud of ultra-cold atoms, consider that you are part of this strange and wonderful universe. The same quantum laws that allow light to be stopped govern the chemistry of your cells, the firing of your neurons, the very atoms that make up your body. You're a quantum being in a quantum universe, even if you rarely notice it. And in moments like these, when science achieves something that seems like magic, you're reminded of the deep mystery that underlies even the most ordinary moments of existence. The laboratory where light was first stopped has returned to normal temperature and pressure. The scientists have moved on to new experiments, new challenges. But for those 60 seconds, that small space contained one of the universe's most remarkable phenomena. Light itself, the cosmic messenger, the fastest thing that exists, held perfectly still. It was a moment when human understanding touched something fundamental about reality, when we proved that even the most basic assumptions about the universe can be transcended with the right knowledge and tools. Tomorrow, somewhere in a laboratory, light will be stopped again. It has become almost routine for those who work in quantum optics, another tool in their experimental toolkit. But the wonder of it never quite fades. Each time light stops, it's a small miracle, a violation of our deepest intuitions about how the universe works, a reminder that reality is far more interesting than we imagined. The photons that were stopped in that first experiment have long since continued on their way, absorbed by detectors or walls, or simply scattered into the thermal background of the universe. But their pause, their 60 seconds of stillness, changed something fundamental in our understanding. They proved that light, which has traveled freely since the first moments after the Big Bang, can be convinced to rest, to wait, to exist in a state that shouldn't be possible but is. This is the gift of science. Not just knowledge but wonder, not just understanding but mystery. Each answer reveals new questions, each achievement opens new possibilities. Stopped light is both a culmination of centuries of scientific progress and a beginning, a doorway to new physics, new technologies, new ways of interacting with the universe. As you finally drift into sleep, carried by the gentle rhythm of your breathing, the slow beat of your heart, remember that you exist in a universe where light can be stopped, where the impossible becomes possible with the right understanding, where human curiosity and ingenuity can unlock secrets hidden since the beginning of time. The universe you'll wake up to tomorrow is the same one you're leaving tonight, but your understanding of it has changed, deepened, expanded to include this quiet miracle of stopped light. The sodium atoms that held light still for those 60 seconds were ordinary atoms doing something extraordinary, just as you are ordinary matter, capable of extraordinary thought, extraordinary dreams, extraordinary understanding. We are all part of the same quantum dance, the same cosmic choreography that allows light to race through space or stand perfectly still, that allows matter to exist as particles or waves, that allows information to flow through time or pause outside it. In your dreams tonight, perhaps you'll imagine light stopping all around you, photons pausing mid-flight like snowflakes frozen in air. Perhaps you'll dream of the ultra-cold laboratory where atoms barely move, where quantum effects dominate, where the impossible becomes real. Or perhaps you'll simply sleep, peacefully unaware, while all around you light continues its eternal journey, carrying information across the universe, connecting stars to planets, the past to the future, just as it has since the beginning of everything. But now you know that this eternal journey can be interrupted, that light's relentless motion can be paused, that even the most fundamental aspects of reality contain hidden flexibility. This knowledge changes nothing and everything. The universe continues as before, but our place in it has shifted slightly. We are no longer just observers of light but conductors of its motion, able to stop and start the cosmic messenger at will, partners in the dance between energy and matter, motion and stillness, time and timelessness. And so, as consciousness fades into dreams, as your thoughts slow and stop like light in that quantum cloud, you become part of the same mystery you've been contemplating. Your awareness pauses at the threshold of sleep, suspended between waking and dreaming, holding today's thoughts and tomorrow's possibilities in perfect quantum superposition. In this moment, you understand something beyond words, that stopping and starting, motion and stillness, light and darkness, are all part of the same cosmic rhythm, the same universal dance that continues whether we're awake to witness it or lost in dreams. The universe doesn't need us to stop light. It has been creating and destroying light for billions of years without our participation. But by learning to stop light, we've joined the cosmic conversation in a new way. We've proven that consciousness and curiosity can unlock possibilities that pure nature, for all its power and beauty, rarely explores. We've shown that the universe becomes more interesting, more complete, when intelligent beings within it learn to manipulate its fundamental forces in new ways. Stopped light is our contribution to cosmic evolution, our small addition to the universe's repertoire of phenomena. For 60 seconds in a small laboratory on Earth, we created something new under the sun. Or rather, we stopped something as old as the sun itself. It was a quiet revolution, unnoticed by most of humanity, but profound in its implications. We touched the untouchable, stopped the unstoppable, and in doing so, expanded the boundaries of the possible. Sleep now approaches like a slow wave, like light entering that cloud of ultra-cold atoms, slowing down, until finally everything stops. Your thoughts pause at the edge of dreams, held in the quantum suspension of near sleep, perfectly preserved until morning when consciousness will resume its journey. In this pause, in this moment between moments, you're like that stopped light, information temporarily removed from the flow of time, waiting in perfect stillness for the signal to continue. The 60 seconds of stopped light have become hours of contemplation, of wonder, of gentle exploration of what it means that such a thing is possible. Time has stretched and compressed, moved quickly through exciting ideas and slowly through deep mysteries. Like light itself, our journey through these ideas has sometimes raced ahead, and sometimes paused to examine particularly beautiful or profound concepts. And now, as this exploration comes to its close, as the narrative light of these words prepares to stop, consider one final thought. The scientists who stopped light didn't destroy it, or capture it in any permanent way. They simply asked it to pause, to exist differently for a moment, to demonstrate the flexibility hidden within natural law. When they released it, the light continued exactly as before, carrying its information forward as if no time had passed. Nothing was lost, only something wonderful was gained. The knowledge that even light, even the fastest and most fundamental messenger in the universe, can be convinced to stop and rest. You too can rest now, knowing that the universe is full of such wonders, full of phenomena waiting to be discovered, full of impossible things that become possible with the right understanding. The light that has carried these words to your eyes can now fade. The thoughts that have followed this narrative can now slow and stop. The consciousness that has been exploring these ideas can now pause, suspended in the quantum state of sleep, perfectly preserved until morning when the journey continues. In the grand symphony of the universe, where galaxies spin and stars burn and light races through the void, we've learned to add our own notes. The pause, the rest, the moment of stillness that makes the motion meaningful. We've learned that the universe is not just a machine running according to fixed laws, but a vast jazz performance where improvisation is possible within the structure, where new variations on ancient themes can still surprise and delight. The stopped light experiments continue in laboratories around the world. Scientists are pushing the boundaries further, stopping light in new materials for longer times, with greater precision. Each experiment adds to our understanding, our control, our partnership with the universe. What started as a wild dream, an impossible goal, has become another tool in humanity's ever-expanding toolkit for understanding and manipulating reality. But beyond the practical applications, beyond the technologies that might emerge, the simple fact that we can stop light has already changed us. We know now that we live in a universe more flexible than we imagined, more open to negotiation than we thought possible. We know that the cosmic speed limit can be temporarily suspended, that the eternal journey of light can be interrupted, that even the most fundamental phenomena can surprise us with hidden possibilities. This knowledge becomes part of humanity's intellectual heritage, passed down to future generations who will build upon it in ways we cannot imagine. Children born today will grow up in a world where stopping light is a known possibility, where the impossible has already been achieved. They will dream different dreams, imagine different futures, push against different boundaries. The stopped light of today becomes the starting point for tomorrow's miracles. As you finally surrender to sleep, as your consciousness stops like light in that quantum trap, remember this. You live in a universe where wonders never cease, where curiosity is rewarded with miracles, where the impossible becomes possible for those brave enough to try. The light may stop, but the wonder continues. Time may pause, but discovery moves forward, and in that forward motion, in that endless exploration of what's possible, we find meaning, purpose, and endless reasons for quiet amazement. Good night, fellow traveler, in this strange and beautiful universe. May your dreams be filled with stopped light and quantum mysteries, with the wonder of discovery and the peace of understanding. And when morning comes, when consciousness resumes its journey like light, released from its quantum trap, May you wake with a renewed sense of awe at the universe we inhabit, where even light itself can be convinced to pause its eternal journey, to rest for a moment in our gentle quantum embrace, before continuing on its way through the vast and wonderful cosmos we call home. End.